I'm not going to give an epistemological talk. It's a talk about physics and just the way I use the concept of non-locality. So quantum technology, how did they emerge? There is a discussion between Einstein and Bohr, and in addition, Schrödinger adds his grain of salt, and with all of that, the conclusion was that entanglement is amazing. And then they had to wait another 39 years, and John Bell came, and to make a long story short, the conclusion of John Bell is entanglement is different. Different of what? Different of the way people were thinking about quantum mechanics, and in particular the linearity of quantum mechanics. Everybody was thinking of the linearity of quantum mechanics, but I am not sure, and probably people had not realized that the application of this linearity of quantum mechanics about two entangled objects at a distance really raised a completely new question. Another 20 years, and Feynman in 1982, there is this famous paper of Feynman, which is simulating physics with computers, in which Feynman first acknowledges that he had missed the importance of entanglement. If you read lectures on physics, which was published in 1960 or 59 or 60, Feynman addresses the question of EPR and say EPR is nothing else than what we have seen about interference of a single particle. And in 1922, Feynman say, oops, I missed the point. And entanglement is really something different. And Feynman being Feynman, as soon as he say this is new for me, he invents a way of using it, and he raises the basis of quantum computing. So what I am going to show you, I'm going rapidly to rephrase the EPR reasoning in the version of Bohm, which is the one that everybody uses and the one that you need to have to derive Bell's inequalities. Many people missed that point. You need to have dichotomic variable. Can be a spin 1/2, can be polarization of a photon, but you need dichotomic observables. So I'm going to derive that, and then we will go on until Gautier stops me. So Einstein was asking the question. We all know that Einstein was annoyed by the probabilistic character of quantum mechanics. Of course, Einstein had no problem with statistical physics. You know his famous paper about Brownian motion. But he thought that it was a convenient tool, statistical physics, but that the bottom had to be non-probabilistic. And so he was asking the question, is it possible to explain the probabilistic character of quantum prediction by completing quantum mechanics at an underlying more precise level of description? And you can call that level supplementary parameter, hidden variables, etc. It's clearly the same kind of reasoning as to say, if I have a Maxwell-Boltzmann distribution for the molecules in this room, in fact, I think that each molecule has its own trajectory, etc., and that the statistical description is convenient, but is not fundamental. And so Einstein tried to find situations in which the very laws of quantum mechanics allow one to precise, for instance, position and velocity better than what is allowed by the Heisenberg relation, what I call Heisenberg dispersion relation. By the way, I don't like the more principle of uncertitude, because it's not a principle. It's a consequence of the mathematics. It's mathematical relations, dispersion relation, which are a consequence of the principle, does not derive from anywhere. Okay. And so Einstein tried to find situation in which the quantum calculations allowed you to precise position and velocity better than allowed by this. He first tried with single particles, Gedanken experiment. It was in the Solvay conference in 1927. He said, oh, look here, I can define the velocity and the position better than allowed by Heisenberg relation, but at the end of the day or at the end of the night, next morning, Bohr would come and say, no, this does not work. And we can say that Bohr always replies satisfactorily to Einstein in this Solvay conference. But in 1935, Einstein got to the famous Einstein-Podolsky-Rosen-Gedanken experiment with two entangled particles, and not only two entangled particles at a short distance, but two entangled particles with a separation. And then, in my opinion, everybody can make his own opinion because the papers are published in a physical review. It's very easy to find them. In my opinion, the reply of Bohr to Einstein is considered as valid only by people who have already totally adhered to Bohr philosophy, okay? Okay, so what is the experiment? Everybody knows this experiment, but I just precise. I have a photon U1 going to the left, a photon U2 going to the right. They don't have the same color, so don't look for anything like indistinguishability in this experiment. And you make here a polarization measurement, which is a dichotomic observable. The polarizer can be oriented, and you have an orientation defined by the unit vector A. And when the polarizer is oriented along A, you can get either result +1 associated to the polarization along A, or result -1 associated to polarization perpendicular. Same thing on the second polarizer. And if now you have many pairs and you repeat, well, one pair at a time, but you repeat the experiment many times, what can you obtain at the end? You do statistics and you obtain probabilities. So you can obtain the single probabilities to get +1 or -1 here, but much more interesting, of course, the joint probability. Probability to get +1 here and +1 here. And you call it P++ of AB, because you have to say what are the orientation of the polarizers. So this is just a description of an experiment. You don't need any quantum mechanics to, well, you need a little bit of quantum mechanics to accept the idea that the photon is a particle, but it could be spin 1/2. Well, you need also quantum mechanics. Okay, but okay, it's not yet EPR. EPR is if you have a state for describing the two particles, which is like that, and even people who don't know very much the formalism of quantum mechanics can easily understand what it means, XX would be a pair of photons polarized along the direction X, YY would be a pair of photons polarized like that, XX plus YY is an entangled state, which means that I cannot develop it mathematically and present it as a product of a certain state for the first photon and a certain state for the second photon. It's impossible. Don't think that it is, for instance, at 45 degrees or something like that. And at this point, it's almost as surprising as the Schrödinger cat, which is both dead and alive, except that there are only two photons, and in Schrödinger cat, yeah, there is more than two photons, of course. But conceptually, it's the same kind of problem. How can we think of something which is both this and that? That's a problem for you. So once you have that, it's an elementary exercise in quantum mechanics to calculate the various probabilities, and the single probability are 1/2, which means that whatever the orientation here, you have 50% chance to find +1, 50% chance to find -1. It's just like a game of tossing a coin. Same thing on the other side, but when you calculate the joint probability, you have something which is very interesting, because here, for instance, if I make the angle between the two polarizers equals 0, then the probability P++ is equal of 1/2. And I claim that there is a total correlation. You are going to say, no, 1/2 is not total. Yes, 1/2 is total. Why? Because the probability to have +1 is 1/2. And if you have the joint probability to have +1 and +1 is also 1/2, it means that the conditional probability to have that one, if you add this one, is 100%. And if you are not yet totally convinced that it is an interesting situation, the cross probability P plus minus is 0. So it means here it looks totally random, here it looks totally random, but if you have +1 here, you have +1 here, if you have -1 here, you have -1 here. The reasoning of Einstein, Podolsky, and Rosen at this point consists to say, we know that what will be found here is the same as what is found there. And the reasoning of Einstein, Podolsky, and Rosen was to say, because we know that, and because it is at a distance, the relativistic argument is crucial in that. Because the two measurements at a distance, if we know for sure that they are the same, we don't need to do the measurement here. We know in advance what will be the result there. And they concluded that quantum mechanics has to be complete. And so I want to insist that relativistic separation is really at the root of Einstein-Podolsky-Rosen reasoning. If the two particles were on top of each other, nobody would, well, I don't say nobody would care, but it would not be, and the EPR reasoning would not work. The EPR reasoning is based on relativity, and I have two citations, one from Einstein in the famous book Philosopher Scientist. On one supposition we should, in my opinion, absolutely hold fast: the real factual situation of system S2 is independent of what is done with system S1. And the reason why he said that, it's because of relativity. And Bohm and Aronoff have something similar, but let me go on. Bell theorem. I like this photo. I like also a similar photo which is on your handbook, because this experiment is my experiment. So you know, Bell is really a personality. First, he shows that the von Neumann proof that you cannot have hidden variables is false. There are not many people who have found a mistake in von Neumann, okay? So it was a good start. Then he writes this paper, okay, in which he will find that there is a way to show a contradiction between quantum mechanical prediction and completing quantum mechanics with hidden variables is to assign a property that he calls locality to the hidden variables. So the idea is the following. In order to explain this correlation at a distance, you just admit that the two photons share a joint property from start, okay? And this joint property that we call lambda, that he calls lambda, will determine the result of the measurements. It's not complicated to understand that it's a good way to understand correlation. It's an image which is used all the time in science. For instance, if you have two twin brothers, similar, same, I don't know how they say, same twins, okay? Homozygote. If you observe, suppose they are born here, and then one goes to America, one goes to Australia, and when the age is 20, you observe the color of the eyes. They have the same color of the eyes. No surprise, they have the same chromosome. Maybe one develops genetic disease, and the other one will develop it. No surprise. So to understand correlation by a joint property from the production of the two particles is very natural. One may think that it is a good way to understand quantum mechanics. But at that point, Bohr disagrees, and Bohr disagrees because I would say after reading him so many times, I think that he had the strong intuition that quantum mechanics would fall apart, that the self-consistency of quantum mechanics would be ruined if he would accept that. But he did not demonstrate it. It's Bell who demonstrated that. So we have to give the credit to Bohr that he certainly had the intuition, and we must give the credit to Bell that he demonstrated it. And Bohr thought that quantum mechanics was complete, and as soon as you introduce supplementary parameters, you complete it, because in quantum mechanics all the pairs are described by the same state that I've written already, 1/√2 of x plus yy, while here you add something different for each pair. The lambda is different for each pair. The formalism, he uses a formalism in which you have a function capital A dichotomic, can take only value +1 or -1. to describe the result of the measurement at first polarizer. Capital B describe the result of the measurement at the second polarizer, and of course you must have a distribution for the probability distribution for the supplementary parameters lambda, and once you have that, you can calculate the correlation coefficient, which takes this simple value. It's a usual definition, okay? Average of the product minus product of the average, and you normalize, but it turns out that the product of the average is 0, and when you normalize it's 1. So it takes this simple form. And I like to show this very simple example. It's an example that any of us would think of after thinking more than 5 minutes, okay? Some of us are faster and would find it in 2 minutes. You assume that it means something, that the photon has a certain polarization. And then if the polarizer is like that, you get +1. If it is like that, you get -1. And you must have a frontier, because once again it's dichotomic, and you put the frontier at 45 degrees. And that's all. And with that, so the function which is here, I'm sure that Jean-Pierre has already seen that it does the job, okay? And when you use that, you find the red line, which is not bad from the quantum prediction. It gives full correlation at 0 degree, full correlation at 90 degree, and it's not so far. And so the question, you may think, okay, with a little more sophistication, you are going to be able to find a model agreeing with quantum mechanical prediction at all orientations. And Bell's theorem just say, no, it is not possible. So Bell's theorem, so no local hidden variable theory in the spirit of Einstein's idea can reproduce quantum mechanical prediction for EPR correlation at all orientation of polarizer. This is how it works. There is a quantity S, which is associated with 4 measurements. You take 2 direction A and A prime, 2 direction B and B prime, and you make measurement for AB, AB prime, etc. 4 possibilities. And then you write this strange combination, 3 plus, 1 minus, 1. Why 1 minus? I don't know. Just as a question why John Bell was a genius. Okay, he had a good idea. Okay, and then I have here a demonstration which is extremely simple. It does not take more than 2 minutes, but I will pass, and if you want, I will show you in private, or maybe if you ask questions later. And then the demonstration is really high school mathematics demonstration. But Bell's theorem says that this quantity cannot be bigger than 2, cannot be less than -2. And if now you take the quantum mechanical prediction, which is written here, for this angle, here is pi over 8, and pi over 8, cosine of 2 times pi over 8 is 1 over root 2, so you have 1 over root 2, 1 over root 2, 1 over root 2, and here is 3 pi over 8, you double, it's minus 1 over root 2, and so you get more than 2. This is Bell's theorem. You cannot mimic, reproduce the quantum mechanical prediction at any angle, and in particular you have a counterexample. You have a situation in which you cannot mimic quantum mechanics with a local hidden variable theory. It turns into an experimental equation, but before going to the experiment, I want once again to, not once again, I want to think for 1 minute about where we are. We think of completing quantum mechanics with supplementary parameters carried along by each particle. This is what is some kind called Einstein local realistic view. Why? Because Einstein clearly thinks that when you have a system which is localized in space-time, when Einstein writes space, it clearly means space-time. When you have a system which is localized in space-time, he thinks that in that volume of space-time, you have all the properties that will determine any measurement you will do on that system. So you have the lambda here, it will determine everything. Okay? So this is called Einstein local realist worldview. In order to demonstrate, in addition, Bell, so you first assume that, so you introduce lambda or the the simplest way to render an account of Einstein position is to introduce a lambda. And then the locality condition that Bell found necessary to find the contradiction is the fact that the result of the measurement here cannot depend on the orientation of the orientation here, which can be written mathematically as saying that the function capital A cannot depend on B, and reciprocally capital B cannot depend on A, and of course also you need to have the way in which the pair are emitted does not depend on the orientation of the polarizer. All that makes sense, but what Bell emphasizes in the conclusion of his paper, and this sentence changed my life, because when I read that, I say, this is what I want to do. Bell says, if you could change the orientation of the polarizers while the photons are in flight, then the locality condition would no longer be a reasonable hypothesis. It would become a consequence of relativistic causality. That's it. So now, experimental test. So an experimental test is possible, but one must find a situation where the test is possible. I showed you one with the photon polarization and the angle pi/4, but this was found by Clauser, Horn, Shimony, and Holt. The initial paper of Bell was more a paper of a theorist, okay? So Clauser, Horn, Shimony, and Holt make a proposal for a real experiment, and now I'm going to give a very fast overview. I like to say that there are three generations of experiments. The heroic pioneers in 72, 76. There was first Clauser in Berkeley, Clauser and Friedman, and Pipkin and Holt in Harvard. Clauser found a result in agreement with quantum mechanics and violating Bell's inequality. Pipkin and Holt found the result not in agreement with quantum mechanics and agreeing with Bell's inequality. But it rapidly became clear that the experiment of Clauser and Friedman was a better experiment in the following sense. You could really change many parameters and observe how it evolves. In the Pipkin experiment, it's an experiment which is frozen. The only thing that you can do is repeat it or maybe kick it, but there is no parameter, no knob you can turn, okay? So from this point of view, the Clauser and Friedman was more convincing. And after a few years, there was a clear trend in favor of quantum mechanics. Clauser repeated the experiment of Pipkin and Holt and found quantum mechanics. And Fry in Texas in 76 did an experiment in which there was for the first time a laser. The signal to noise ratio was better and the results were about the same. All these experiments, after a few years, were reasonably convincing in favor of quantum mechanics, but all these experiments were significantly different from the ideal scheme I have described on which the theorists discussed. And this is the reason why I embarked in 75 into experiments in order to develop experiments with scheme closer and closer to the scheme discussed by theorists. And then there was a third generation. I will say a few words about that. It started in the end of the 80s. Okay, so just to give you an idea, the experiment that started in 75 but was carried out in Orsay, the first one was in 81. So you see the source is very complicated. We have 3 lasers, an atomic beam, etc. It's really a complicated experiment. But the idea is to use this radiative cascade. These are levels in calcium. These had been identified by Clauser and Friedman. And the point is that Clauser and Friedman could not excite easily that level here. And when I started thinking about that source, there were a fantastic experiment here, close to here, by Cagnac, Rembert, and Birabin about the possibility to use 2 photons to excite directly a state like that. So I could, not this one, but I could apply this concept of 2 photon excitation to excite directly that state, selective excitation, and when the atom is here, it has no choice. The only thing the atom can do is to send the 2 photons which are here. It was not the case in Clauser and Friedman. There were many parasitic routes. And to go from here to here, you have two possible paths. And as usual in quantum mechanics, when you have two paths, you must add the amplitudes. Here it's written with polarization, with circularly polarized photons, but then you change bases and you obtain the state you want. It's wonderful. And it was indeed wonderful. I give here the numbers. 100 coincidence signal in 1 second. And you have to know that in this kind of experiment there is absolutely no noise. Because of this narrow correlation, you eliminate all noise. So the only uncertainty, here is really an uncertainty, is a statistical uncertainty. And so it's just a great number, a Poisson law. So if you accumulate for 100 seconds, you have 10 to the 4 event, and the precision is 1%. In less than 2 minutes, you have 1% precision. It was fantastic. It was order of magnitude better than Clauser. For Clauser, it took days. And for Frey also, it took hours and hours. Here, a few minutes, and it was working. And so this was, so we were using pile of plate polarizer, which is only one pass polarizer, which is annoying, but it was like the previous one. But we tested something which is interesting, the so-called Fourier hypothesis. There were people who would say, okay, entanglement, we understand entanglement. And as a matter of fact, if you want to understand the levels of the helium atom, you know there are 2 electrons in the helium atom. If you want to understand the structure of the level of the helium atom, you have to think of entangled state. But it was at short distance. So some people would say, okay, entanglement exists at microscopic distance, but not at macroscopic distance. And so you ask the question, what is the scale? And they scratch their head and say, okay, the only available scale is the coherence length of the photon. And the coherent length of the photon was 1.5 meter. So I pulled the polarizer at 6 meters, and it was still violating Bell's inequality. Okay. But it was the only new part of that experiment, except for the beta signal-to-noise ratio. Then comes the first new experiment. As I told you in previous experiment, people, and us also for the first one, had only access to that result, and the other polarization, the other result was absorbed. So you don't have access to the minus result. And what do? Well, theorists are smart people, and they tell you, look, you are going to measure without any polarizer, then you measure with the polarizer, and the difference is the minus result. It's not stupid. I mean, but it introduces some new hypotheses, and for this reason, it was much better to be able to develop an experiment like that. I think that it is now long ago, so I can say that I had to bribe some people in the physics research labs to construct for me this polarization split specifically, because nowadays you can order it, okay? You have on shelf, etc. But at that time, they calculated it. Just to give an idea, there are 34 layers of dielectric with wave control, index of refraction, etc. When I ask how much I owe, they say, you cannot pay, it's too expensive. So I gave them a few bottles of wine, and it worked. So this is, you see, there are 2 detectors, one here and one here. And I just emphasize the fact that each detector has a lead shield, etc. It's dozens of kilograms. Okay. The beauty of this experiment is the following. You just put the system as it is. You choose an orientation A and orientation B. You have a run of 100 seconds. During that run, you have 4 results, n plus plus, n plus minus, n minus plus, n minus minus. And that's all. No calibration. You just write this ratio. So in the numerator, you have similar result with a sign plus, cross result with a sign minus, and the denominator is just the sum of the 4. It's self-calibrated. That's the beauty of that experiment. Frank encouraged me very much to do. You remember, Frank, you were a fan of this scheme? And the result is unbelievable. Well, we have to believe it, but the result, let's say, is beautiful. The green curve is a prediction of quantum mechanics taking into account all the small defects. Last experiment, we want to change the orientation of the polarizer while the photons are in flight, and turning something like that, which weight of 30 or 40 kilograms, we cannot do it. So the idea was to introduce here switches able either to let light go in this direction or to redirect it. Here you put a second polarizer, so now you go from A to A prime back to A prime just by switching here. Same thing on the other side. We did the experiment. It was not as impressive as the previous one. Anyway, we violate Bell's inequality by 5 standard deviation. I forgot to say that with two paths we violated by 50 standard deviation. But here, okay, 5 standard deviation, signal was not as good, etc., etc. For the first time, Einstein causality was enforced. So third generation experiments, they were able to produce photons in well-defined directions so they can fill them into optical fibers. And then optical fibers, you can go at hundreds of meters like Zeilinger or even tens of kilometers. And this is Giseng in Switzerland. He uses a commercial network of Swiss Telecom, their optical fiber, and he can go at 30 or 40 kilometers. It's amazing. So nowadays we can consider that all the loopholes have been closed. You know, there is a lot of discussion. I will not speak about it, but I emphasize the fact that I've written a News and Views, but not in Nature, because I had some conflict with them, so I've written it for the American Physical Society, Physics. It's online, and I have a long paper about how to discuss these loophole-free experiments. What can we conclude? Well, we can ask Einstein. I want to emphasize this point. So you may be surprised. So we are going to ask Einstein about the failure of his vision? Yes, Einstein made reasoning ad absurdum. He said, if I was not right, this is what you would have to swallow. And these are the words of Einstein. Either drop the need of the independence of the physical reality present in different parts of space, or accept that the measurement on S1 changes instantaneously the real situation of S2. This is called quantum non-locality, but it can also be called quantum holism. Quantum holism is an important concept for the following reason. Quantum holism means that there is more in the two entangled particles than in the sum or reunion, call it as you want, of the first one and the second one. And these are the root of the power of quantum computing. But what I want to develop in the last 5 minutes is, you told me 5 minutes, is the fact that non-locality is, for me, a very useful image for my intuition. So I show you what I mean. Now, the only conclusion that I have here is that I can describe what happens with standard quantum mechanics by considering that I have first a measurement here and then a measurement there. And then the description using the projection, postulate, etc. is the following. Here, until the last moment, I can have either plus or minus. But if I have plus, then instantaneously the photon on the other side adopts the same orientation. And if I have minus, then at the moment of the measurement, instantaneously the second photon adopts that. This is that image that I use for my intuition, okay? So I want to apply that to quantum cryptography. The problem of cryptography, not quantum at all, there is an absolutely reliable method which is the following. Alice and Bob, where is Alice? Alice and Bob on the other side want to communicate, and there is an awful spy, an eavesdropper, who is here. And the absolutely safe method consists of having a similar random suite of 0 and 1 for Alice and for Bob. Alice uses this random series of 1 and 0 to encode, and Bob uses the same one to decode. So the problem boils down to distributing to Alice and Bob the same random series of 0 and 1 without the spy being able to observe it. And to make a long story short, this is how it works. Alice and Bob do measurements. Sometimes the polarizers are along the same direction, sometimes they are not. But they do the measurement with entangled photon, and they note everything, okay? And then later, with the public radio, Alice will say, this was my orientation, and then Bob say, okay, this one we discard. This was my orientation, and Bob say, oh, I use the same one, so we keep it. And they can do that exchanging radio. The point based on non-locality is the following. Is there anything to spy here for the eavesdropper? No. Because if you believe in my story, okay, that until the last moment, nothing has happened. It's only at the last moment when the measurement takes place here that it is decided whether it is +1 or -1. In between, there is nothing to spy. And so, by this intuitive image, I know immediately why this method, which is the Eckert method of quantum cryptography, is good. Then I can develop calculation, etc. But immediately, by that image, I know that I know the value of this. And just to say that the Chinese have put a source of entangled photon in a satellite, and they are able to distribute entangled photon at more than 1,000 kilometers. I just want to say, one word. C'est bon, it's enough. One word about my intuition based on non-locality for quantum teleportation. Quantum teleportation, of course, is not Star Trek. It's having a state here transported, teleported onto an object which is here. And this is very surprising because you know that there is absolutely no way to fully know a quantum state. If you have only a single object, you can only have one projection on something. You cannot have the full. But here, we are not going to have it. We are just going to erase it here and transport there. So I pass, I make a, there is a no cloning theorem, etc. I just go to the end to explain you what is the point. The idea is the following. I have here the photon of which I want to transport the polarization. I have it interacting with one of two entangled photons. I have a pair of entangled photons. It interacts by a beam splitter and then a so-called Bell state measurement. Don't ask me, but it's only 4 results possible, so you can encode the result, which is now classical because you have a result, okay? And you can encode it on 2 bits. You send it here, and then you operate a transformation on the second photon, and now the state which was initially here is transferred until the other one. So this is the scheme. But if you believe in the story that when the measurement is done here, instantaneously the photon U2 which is here is transformed, you have a problem because this takes time. It's a classical channel. So you have to put the second photon on hold, waiting for the classical signal to arrive. And this is what Nicolas Gisin has done by adding a long optical fiber. But most of the people who claim that they have done quantum teleportation don't do that. They cheat, in a sense, because they post-select only cases where you don't need to transform. Read the paper. Frank looks at me, he's surprised. I found that because I was writing a problem about quantum teleportation for my students at Polytechnique. And by writing the problem, I realized this point. I wrote to the author of the teleportation paper, and they confirmed. So, you need, and this tells you one thing. Not too many young people here. When I have many young people, I'll tell you something. There is one big advance which is absolutely demanded in quantum technology, a good quantum memory. If you have a good quantum memory, there are very beautiful things you can do, including having real quantum teleportation. So, okay, conclusion, blah, 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 blah. Non-local image, this, in relation to epistemology, non-local images give fruitful intuition for quantum technology to be checked by the standard formalism of quantum mechanics. I don't say it's real or it's not real. I know it is useful for my intuition, and you can debate it, you who are thinking of epistemology. Thank you very much.